Previously, I've mentioned dependent sources, but we've never used them. In this video, I'll talk about modeling op-amp circuits as dependent sources and how to analyze circuits that contain dependent sources. The operational amplifier model I presented in a previous video looked like this. There's an input resistance between the two input terminals, and the voltage across that resistance is used to control a dependent source that creates the op-amp output voltage. What I'm going to focus on in this video is that this model represents the internal circuitry of the op-amp as a dependent source. By extension, this means that circuits that contain operational amplifiers can also be modeled as dependent sources. I introduced dependent sources briefly early in this course, but I didn't talk about analyzing circuits containing dependent sources, since we haven't had a way to actually implement a dependent source yet. Now that we have a way to implement dependent sources using operational amplifiers, I want to talk about analyzing circuits that contain dependent sources. But before I talk about that, I'll do a quick review of dependent sources themselves. Dependent sources can provide either voltage or current to a circuit, and that voltage or current can be controlled by either a voltage or a current elsewhere in the circuit. That means there are four possible types of dependent sources. Voltage-controlled voltage and current sources provide a voltage or current that depends on a voltage elsewhere in the circuit. These sources are commonly abbreviated as VCVS and VCCS, respectively. Current-controlled voltage and current sources provide voltage or current that depends on a current elsewhere in the circuit. These are abbreviated as CCVS and CCCS. Symbols for the four types of dependent sources are shown here. These dependent source models are all linear. A voltage-controlled voltage source outputs a voltage that equals some number times a voltage elsewhere in the circuit. A voltage-controlled current source provides a current that is proportional to a voltage elsewhere in the circuit. A current-controlled voltage source provides a voltage that's some number times a current elsewhere, and the current-controlled current source provides a current that's controlled by a current elsewhere in the circuit. As an example of representing an op-amp circuit as a dependent source, let's look at this inverting voltage amplifier. The input-output relationship for this circuit is that the output voltage is equal to the negative of RF over Rn times the input voltage. Since the output is a voltage that depends upon another voltage, this is a voltage-controlled voltage source. This circuit has the same input-output relationship as our inverting voltage amplifier. The output voltage here is the negative, based on this inversion of polarity, of RF over Rn times Vn. The current provided by this voltage source is also the same between these two circuits. Since this voltage is 0, the current out of the source is just Vn over Rn. Ohm's law in this circuit says that the current out of the source is also Vn over Rn. Analysis of circuits containing dependent sources is very similar to what we've already been doing. Kirchhoff's laws and Ohm's law are still the basis for any analysis, and their extensions to nodal and mesh analysis are also still applicable. The only big difference is that there are typically additional equations as necessary to model the dependent sources themselves. We also need to keep in mind what we don't know about these sources. As with independent sources, we don't know anything about the current through a dependent voltage source or the voltage across a dependent current source until we actually analyze the circuit to which the dependent source is connected. Now let's do a couple of examples of the analysis of circuits containing dependent sources. In this example, I want to determine the current I in this circuit that contains a voltage-controlled voltage source. All of these elements are in series, so they all share the same current I. If I do KVL around this loop, negative 12 volts plus this voltage, V1, minus 4V1, plus this voltage, which is going to be just 8 times I, is equal to 0. That's one equation with two unknowns. I need another equation which is given to me by the source itself. So V1 is equal to 6 times I. If I plug this in here and here, I get minus 12 plus 6I minus 4 times 6I plus 8I is equal to 0. So 12 is equal to 6 minus 24 plus 8 is 10 with a negative, so I is equal to negative 1.2 amps. In this circuit, which contains a current-controlled current source, I want to find this voltage V across the 4 amp source. All of these elements are in parallel, so they all share the same voltage difference V. If I do KCL at this terminal and assume that positive currents are leaving that node, this becomes a negative 4 amp contribution plus I1 is leaving the node minus 3 times I1 plus this current, which is just V over 2 ohms. That sums to 0. I have one equation and two unknowns. I can get another equation from the definition of I1. I1 is just equal to this voltage V over 6 ohms. If I plug that in here and here, and take 4 amps to the other side, 4 amps is equal to V over 6 ohms minus 3V over 6 ohms plus V over 2 ohms. This and this cancel out. 3 over 6 is 1/2. If I multiply through by 6, V is equal to 24 volts. One major difference between the analysis of circuits containing dependent sources and those with only independent sources is in determining the Thevenin equivalent resistance of the circuit. Dependent sources can't be killed the way independent sources can. I'll talk about that next.